All right, let's talk about three words you use literally every day: temperature, energy, and heat. You think you know what they mean, but I promise you, by the end of this, you're gonna understand how a giant frozen glacier can actually have way more energy than a single burning match.
So let's just dive right in with that puzzle. Which one has more thermal energy? A massive, sprawling glacier, or one little match? I know, your gut instinct, your common sense is probably screaming, the match, obviously. But, well, physics has a surprise for you.
And look, this isn't some kind of trick question or a riddle. The answer is hiding in plain sight, in the real, physical meaning of these simple words. To find it, though, we have to zoom in. I mean, way in.
So let's start with the secret life of particles. It's all about how the tiny explains the mighty.
Okay, the one big idea you need to get your head around is called the kinetic theory of matter. It's actually pretty simple. It just says that everything, the chair you're sitting on, the air you're breathing, all of it is made of tiny particles that are constantly moving, just buzzing with energy. And how they move determines pretty much everything we see and feel. Let's make this super simple. We all know the difference between ice and water, right? On our scale, the macroscopic scale, one's a solid. It feels cold, it holds its shape. The other is a liquid. It feels warmer, and it'll slosh around and take the shape of whatever you pour it into. Straightforward stuff. But here's the crazy part. If you could zoom down to the microscopic level, you'd see they're both made of the exact same stuff. H2O particles. The only thing that's actually different is how much those little guys are moving. In ice, they're all locked into a tight structure, just kind of vibrating in place. In water, they've got more energy, so they break free and can slide and tumble past each other. That's it! The whole difference between a solid and a liquid is just how much the particles are jiggling.
So, if everything is just a big collection of moving particles, how on earth does that get us back to our glacier puzzle? Well, it all comes down to being really precise about three key definitions.
First up, temperature. Now listen closely, because this is the key. Temperature is a measure of the average energy of motion per particle. That word average is everything. It's not the total energy, just the average energy of a typical particle in the group. Next, we've got internal energy. This is different. If temperature was the average, internal energy is the total. You take the energy of every single particle, all their motion, all their potential energy, and you add it all up. This is the whole shebang.
And finally, heat. And this is one we get wrong all the time in everyday language. You see, in physics, an object can't have heat. Heat isn't a thing you can contain. Heat is the process of energy moving from a hotter object to a colder one. It's energy in transit.
So let's really focus on this idea, average versus total energy. This little distinction might seem small, but believe me, it changes absolutely everything.
Imagine we have a little box with just two particles in it. Particle A has 2 joules of energy, and particle B has 4. So what's the average? 3 joules per particle. That's its temperature. And the total internal energy? Well, you just add them up. 6 joules. Simple enough, right?
Okay, now look at this second box. This one has 4 particles, all with different energies. But if you add them all up and divide by 4 to get the average, you get 3 joules. It's the exact same average as the first box. So they have the same temperature. But what about the total energy? Well, that's 12 joules, double the first box.
And this right here is the whole point. You can have two different things with the exact same temperature, the same average particle energy, but because one of them simply has more particles, it can have a totally different and much, much larger total internal energy. This isn't just some abstract idea. You see this in the real world constantly. Think about filling a bucket with water from a swimming pool. The water in the bucket and the water left in the pool are at the exact same temperature, right? The average jiggle speed of the particles is identical, but the pool has trillions upon trillions more water particles than the bucket. So which one has more total internal energy? The pool, by a landslide. It's not even close. And getting this difference between average and total energy isn't just a neat trick. It actually unlocks some really profound truths about how the universe works.
For example, if temperature is just a measure of particle motion, well, it kind of makes you wonder, what happens if you could make all the particles stop moving completely? Well, there's a name for that. It's called absolute zero. Zero on the Kelvin scale. It's the ultimate cosmic speed limit for cold. You literally cannot get any colder than that.
And that leads to this really mind-bending idea.
Unless something is at absolute zero, it is packed with internal energy. That snow you're shoveling, that ice cube in your drink, it feels freezing to us. But on a microscopic level, its particles are still humming along, vibrating with energy.
So what happens when you touch a hot object to a cold one? Well, that energy starts to move. Here, object A has a higher temperature, so energy naturally flows from A over to B until things even out. And that very process, that flow of energy from hot to cold, that's heat.
Okay, we've sharpened our definitions. We've got our new physics mindset. Let's go all the way back to the beginning and finally put that puzzle to bed, the glacier and the match. The tiny flame of the match has an incredibly high temperature for sure. That means its particles have a super high average energy. They're moving like crazy. But the glacier, even though its temperature is low, is just mind-bogglingly huge. It contains an astronomical number of H2O particles. So even though each particle is only vibrating slowly, when you add up that little bit of energy across trillions and trillions and trillions of them, the total internal energy of the glacier absolutely dwarfs that of the match.
So, mystery solved. The glacier has vastly more total thermal energy. Temperature just tells you the average story, but it's the size that tells you the total. It really makes you wonder, doesn't it? What other everyday concepts are we all getting just a little bit wrong?